Hello everyone. So today we will be continuing our discussion with convex mirrors. So in the previous class we saw about the ray diagrams, all the six cases for concave mirrors. We learned about the uses of concave mirrors, and today we will be seeing only two cases in case of convex mirror, because there is not much differentiation in the nature of image as you place the object at different position from the mirror. So we will consider only two cases. First is that the object is placed very far away from the mirror, and the second case when the object is placed very near to the mirror, that is between the focus and the pole. So regarding a concave mirror, let us take the first case where the object is placed very far. That means we are taking the case of infinity. Object is placed at infinity. So if I draw the diagram of a convex mirror now, so as I told you in the last class, that convex mirror somewhat like this. Okay, so here the non-reflecting side is this one, and if I mark the middle of this mirror, that will be somewhere here. Let us say this is your, let us say this will be your pole, and then let us mark the principal axis first. So this is your principal axis, and if I talk about the focus, it will be somewhere, let us say here, and this is, let us, let me draw it. Yes, so this is your center of curvature, this is your focus point, and now this is your reflecting surface. So I am telling that the object is placed at infinity. It means that from somewhere infinite direction, from somewhere infinity, the rays will be coming. So let us say, suppose from infinity some rays coming. Okay, let us take this like this. So from infinity these rays are coming, these rays are coming from infinity, and this is your incident ray. And as I told you that from here you will be drawing the normal. If you draw the normal here, it will be somewhat like this only, right? Somewhat like this. And now if I will be drawing the reflected ray, it will be, the angle of incidence will be equal to the angle of reflection. And I told you in the last class that if the principal axis is seeing a incident ray parallel to it, then this incident ray will be appear to pass from the focus point. So now if I draw the reflected rays, it will be somewhat like this. Okay, it will be somewhat like this, somewhat like this it will be. Okay, and if I draw it in the back direction, it will be passing through the, it appears that it is coming from the focus, because I told you that on the reflecting side only you will be, the observer will be on this side only, on this side only of the mirror. Okay, so this is your reflected ray, right? And now you can see that these rays are coming from focus. If you observe that, if you are observing from this side, it means that these reflected rays, you, it appears to your eyes that these reflected rays are coming from the focus point. Okay, and always I told you that we will consider two rays for this. Let us say some other rays also coming, so that in that case also what will happen, again we will see that it will be passing through the focus point, like this it will be going reflected ray. So on and all, an image is forming at the focus point. So here is the image point. So as I told you, this is like the similar case of a concave mirror when the object was placed at infinity. We told that the image size was highly diminished. Okay, so if I talk about the nature, because see, this is a point size image. Here is where the two reflected rays are appear to be meeting. So if I comment about nature, we can see that the reflected rays are not actually meeting. This is going here somewhere, this is going here. They are not going to meet in the real space. So but if you observe, it appears to your eyes that these reflected rays are appear to be coming from the focus point. So here the virtual focus comes into play, and you can see that a virtual and erect images form virtual and erect image. And if I talk about the size, what is the size? It is highly diminished. The size is highly diminished because you can see the image is point sized. You can tell the image is point sized. Okay, and if I talk about the position, where it is, where is the position? Position is at, it is at focus. It is at focus point. And this is what you can observe in the first case. So we observe that here the virtual image is formed. Now let us take another case, that is the second and the last case, when the object will be placed very near to the mirror. See, this part is what we are saying, that this is focus point and center of curvature. What we do while making analysis, that on both sides of a mirror, suppose this is the pole of the mirror, and we can mark this as the f also. Okay, however the virtual focus is only which will be coming into picture in the convex mirror, but equal to this focal length distance, we are taking this distance as say f also, and I can mark twice of this distance from this f point, that will be c only. Okay, so this will be handy when I will be considering the second case, that is when the object is placed between f and p. Okay, however a mirror has only one focus, but to uh, to specify that where you are placing your object, you need to specify where are you placing your object. So it will be somewhere less than this focal length distance. The object will be less than this focal length distance. Okay, in the next case we will be taking the object distance which is less than this focal length distance. That is the meaning, that is object will be somewhere around here. So let us see the next case. Okay, so now I am taking the case, that is the second case, when object object is placed between f and p, or you can say very near to the mirror. If it is not absolutely right to say f and p, but we can specify this, that let us say let us be more accurate, let us see that between uh, uh, or I can mark this as placed very near to the mirror. Now very near to the mirror means very near to the mirror, the mirror's distance is measured from the pole only. Okay, so now if this is your convex mirror, okay, let me draw a little bit bigger and more accurate diagram. So this is your convex mirror, right? And now this will be somewhere here, your focus your pole will be here, and let us mark the principal axis. Okay, this is your pole, this is your principal axis. Obviously this is your f point, and this is your let us say c point. Okay, so more clear. Okay, now I am placing the object here. Now let us see that I am placing the object here very near to the mirror. This is your let us take a much bigger size of the object. Let us take this one. This is your object AB. Okay, now I will use the diagram ray diagram rules. So if I incident ray, I am taking the top of this object. If incident ray is parallel to this, what will happen? The reflected ray are appear to be coming from the focus point, right? This is the case. This is the case. And the second thing is that when suppose I say I am considering this as the incident ray, this is the angle which is making with the principal axis, then the similar kind of angle it will be making. Okay, so if I draw back trace this, again it will be reflected back, it will be somewhere. You can see that these reflected rays are meeting here. So this is your object. So what you can observe is that if I am talking about the nature of this image, obviously uh, these reflected rays are virtually meeting. They are not meeting in the real, they are meeting on the back side of the mirror. So again the image is virtual, and obviously you can see it is upright. Both the object and image are vertically in the same position, they are in the upright position, so I will say virtual and direct. Okay, and now if I talk about size, now I can say the size at sum was the a dash b is the image. Okay, a dash b dash is the image, so I can see that the image size had somewhat decreased, so I will tell that the image is now diminished. And where is the position of the image? The position of the image is at between f and p. Okay, between f and p, so between these 2 points the image is formed. Okay, so this is your convex mirror. These two only are the cases, and now I will summarize both of these points. Okay, now let us summarize both these points. So we consider these two. This is object position, and now here I will be talking about the image. So one will be image position, image size, and image nature. These are the three things which we need to always keep in mind. Okay, so this is your object. So we consider two cases: when object was at infinity, and the second case very near to mirror. Okay, so what we observed in this case, the position of image was at f, size was highly diminished. Very near to the mirror we see between f and p, and the size was diminished. And in both the cases we saw that the nature was virtual and the image was erect. Now we can see that observe this, that a convex mirror will always be forming a convex mirror will always form a virtual image. This is important, that convex mirror always form a virtual image, and also always the size is diminished. Size is diminished what? If I am will be talking about a term called magnification. So if magnification, that means how much is it enlarged or not. Enlarged means magnified, and diminished is that it is not magnified. Okay, so magnification is less, that means it will be less than 1. We will be studying it further. Okay, so the magnification will be less than 1. That means how you will be distinguishing the mirrors. Suppose I give you two mirrors. Now suppose I give you a mirror. Okay, I gave you a mirror, I gave you a spherical mirror. So I am asking you, identify which type of mirror is this. So what you will do, you will see your image, you will try to see your image on the mirror, and you will try to move the mirror. However, you will be moving the mirror indirectly. What is happening? Object distance is changing. So if you are moving the mirror, it means object distance is changing. And if you are observing an enlarged image, if you observe enlarged image, okay, enlarged image at any point, if you are observing the enlarged image, okay, especially in the concave mirror case, when we studied that when the object is placed very near to the mirror, an enlarged image will be formed. So if you move the mirror closer, if you observe an enlarged image, it means it is a concave mirror. And if you observe the mirror, that always the image is forming is a diminished one. Always the image you are seeing on the surface is always a diminished one. If it is always diminished, if it is always diminished, that means Always diminished means that it is a convex mirror. Convex mirror. A convex mirror will form a diminished image every time. So this is how you will differentiate between these two mirrors. If you take the mirror, okay, you take the mirror, you bring it closer to yourself. If you are seeing an enlarged image, it means it is a concave mirror. If you are seeing diminished image in every time, irrespective of where you are putting the mirror on your face, then it means that it is a convex mirror. Always diminished case is convex mirror. So these are the cases, okay, of the mirrors. So this was all about convex mirrors and concave mirrors. Now, one more important thing is that we must learn some of the formulas, because what will be happening, you need to identify, sometimes there will be a relation between focal length, image distance, and object distance. Okay, so you need to understand these formulae, and then we will be solving numericals. So these formulas will be helpful in determining where the image will be formed, where the object should be placed, what will be the size of image. So that things we will be observing for this mirror. Okay, now let us move further and extend our discussion to this point, and let us discuss now mirror formulae. Mirror formula. Okay, now this is mirror formula. So mirror formula is what? It is a relation between focal length, object distance, and image distance. Okay, that means F is the focal length, U is the image distance, and U is the object distance, and V is the image distance. So these are the general terminologies. Every time, generally these are used to specify this is for the focal length, this is for the object distance, and this is for the image distance. So object distance and image distance are always taken from the pole of the mirror. So before seeing this mirror formula, we must understand first of all what are the sign convention, because we need to understand that how we will be taking sign of different quantities, and sign will determine a lot about the nature of the image. So let us tackle this topic, that is sign convention. For any mirror, let us say I am drawing a mirror here. This is your pole of the mirror, right? Now you know your Cartesian system, right? In Cartesian system, you know that there are two axes. This is your x-axis and this is your y-axis. And this is your origin point. 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 So what you do? From origin to this side is always positive. This side is positive. So first quadrant is always positive quantities are there. Here x-axis is negative. Here y is positive. Here x is again negative and y is also negative. So this quadrant, third quadrant is both are negative. In second quadrant, y is positive. And in fourth quadrant, what happens? X is positive and y is negative. So this is the similar case. You take this pole as origin. Consider this pole as origin of your Cartesian plane. So if you are considering this as origin, first of all, I will draw the principal axis, right? Now this principal axis, you can consider it as your y-axis. Okay, this is your principal axis. Now this you can consider as your y-axis. Consider this as the origin. Consider this as y-axis. This is not y-axis. This is not Cartesian plane, but for learning this sign convention, for remembering this sign convention, we need to learn in this way, that consider this as y-axis. Consider this as y-axis. Okay, and consider this as the origin. Now somewhere perpendicular to this y-axis, this will be your x-axis. Now similar sign conventions will be there. So any distance on this side along parallel to this principal axis, right? Any distance like this. Okay, suppose I am taking a point here, I am measuring this distance, right? Pole is the origin and this is the, suppose an object is placed here. Let us say AB object is placed here and this distance is u. So what is the sign of u? Sign of u is negative. Why negative? Because this is was your origin. I told you consider this as origin. So any distance parallel to the axis, the x-axis, we will be seeing the sign of x-axis. So x-axis on the left hand side, the origin x-axis is what? Negative. So any horizontal distance will be taken as negative. Suppose I am taking an object here, okay, and this image is formed here. Let us say this is a dash b dash is the image. So what you will be taking, suppose now I am considering this distance. Let us say this one. Now I am considering this distance. Let us say v. Now what is the sign of v? In this case, now what is the sign of v? So v is we are measuring on the x-axis, horizontal distance, right? So now from this is right hand side of the region, that means v will be positive. So anything right hand side we will be measuring is positive. On the left hand side it is negative. Now let us see the height of the object. Okay, now please understand that height of the object, we generally height of an object, okay, the height of an object we mark it as h. Okay, we denote as h. So this distance is what? H. This is the object, no? And height of image, we take it as h dash. This is according to your textbook, so it is better to follow the same notations, right? So h dash, so that means this distance is what? This distance is what? H dash, right? Now tell me the sign convention of h. That is the size of image. We call this as height of image or size of image. This is also called as size of object. Size of object. So what is size of object? What is the h sign convention here? Sign notation. See, now this distance we are measuring is parallel to this y-axis. I told you that this perpendicular, this will be your y-axis if this is your origin. Now this is on the upper side, this is on the north side, this is on the top side of the origin. So this distance will be taken as positive because y-axis like this. This is your origin. So any distance here, it is positive. So y-axis h is distance measured in this vertical direction. This is a vertical distance. So that is why h is positive. Now let us see size of image. That is h dash. What is h dash now? H dash is also on the top side of the origin. It is like this. So this is positive. Now let us say instead of this, if I took the object like this, suppose this was your image, this was your a dash, and this is now your h dash, right? This distance is now your h dash. So now what happens? Now this distance is from the downside of the origin, like this, on this side, on this side, on this side. Y is what? Negative. This is your origin, right? And this is positive y, this is negative y. So below the origin, what will be happening? Now if I see this sign, this is not positive anymore. What it has become? This h is now negative. This h is now negative. This is the meaning. Understood? This is the meaning of sign convention, right? Understood? Any distance you can take now. Suppose this is a distance AB, U is negative here, but H is positive. Okay, here V is positive, but H is negative. That is how the things are going to be. Now let us consider the focal length also. Okay, let me continue in this case only. So this is a concave mirror, right? I told you that this is a concave. I am taking this as concave mirror for this time. Both the sign convention will be same. Now always on the reflecting side, I will say that, see, where is the focus? Focus will be somewhere here, right? Now what about the focal length of this? It is on the left side of the origin, right? So what is the focal length of concave mirror? Concave mirror. In case of concave mirror, what is the focal length? Negative. This is important. This is important. What is the focal length in concave mirror? On the left hand side, behind this pole, on the left hand side of the pole, we are having this focus point. So this focal length is negative. Now let me take the example of convex mirror. Okay, let me take the example of convex mirror. Let us clear this better. Okay, so I told you that this was the first case, right? In case of a concave, this was your concave example. So in case of a concave, this was your pole and this was your principal axis, right? So in this case, the focus point was somewhere here, right? So this is your pole. I told you that this should be your origin and this was your focal length. So what is the sign of focal length? In case of concave, it is negative. See this, it is on the left hand side of the pole. Now let us consider the case of a convex mirror. Now this is your convex mirror, right? This is your somewhere here is your pole and this is your principal axis, right? This is your pole, and now what is happen? Curvature is like that. So sphere will be from this side. Okay, so yeah, now this is your focal point. Okay, and we saw that according to the definition also in a concave mirror, when the rays are parallel to principal axis, they are meeting at the point, and that point we call as focus, which is this point. In this case, when the rays are appear to be meeting at a point, that point is this, which we called also as the virtual focus. So this is the focus point of a convex mirror. So what is the distance of focal length now? This is the focal length now, right? This is your focal length now. So you can see that this is your pole, and on the right hand side of this pole we are having the f distance. So what is the f here? This is your convex mirror case. So what is the focal length we are having? We are having a focal length which is positive. So please remember this. These 2 points are important because in the numericals we will be having this discussion. We will be very much be clear about the sign convention of especially this focal length. Okay, so concave mirror, because in some questions of the seeing of only the sign of the focal length, you can guess which mirror it is. Okay, this is the point. So for concave, focal length is negative. For convex mirror, focal length is positive, right? So this was all about your sign convention. Now let us learn about the mirror formula finally, right? Let us begin with the mirror formula. So what is mirror formula is, I told you it is a relation between F, V and U. Okay, where let me specify this because first time I must. This is the object distance from mirror. From mirror means pole of the mirror. Please remember this. V is image distance from mirror, any mirror. Okay, and F is the focal length of, right? So this is your mirror formula. What is mirror formula? It is a relation given by this: 1 by focal length is equals to 1 by V plus 1 by U. This is your mirror formula, right? So by this you can establish a relationship. If two of the quantities are given to you, you can find the third one. This is the relation between focal length, image distance and the object distance, right? So this is your mirror formula. We will be seeing the numerical problems in a while. We will be seeing probably in the next class we must see the numerical problems with all the reflection portion, that is plane mirrors, concave mirror, convex mirror. Okay, all these uh, questions we will be seeing in the next class. For now, just understand this mirror formula. Okay, okay, so please remember this, that u generally always is negative. Okay, we will be taking u, we will be putting the according to the sign convention. What you need to understand is that by the sign convention we will be putting the values here. Okay, suppose this is the case and this is your pole, this is your mirror and object is placed here. Okay, this is your AB. So this distance is image distance is U. So you will put, suppose this U is equals to 8 centimeter here, right? So in this formula, you will be using U is equal to minus 8 centimeter. With proper sign convention, you will be putting here. Okay. So U will be minus 8. So please understand this, that always on the reflecting side of the mirror, you will be putting the object that is on the left side of the mirror. So always U will be negative only. Okay, whether it is a concave mirror, in concave mirror also use negative, in convex also this is the pole, so you will be putting the object on this side only. Yeah, image distance can be positive or negative. Okay, generally you will be negative. Okay, and concave mirror you will be concave mirror, again I am specifying this, in concave mirror you will be getting focal length as negative. In convex mirror you will be seeing the focal length as positive. You will get the with proper sign convention, you will get the focal length. Suppose u is given to you, u is given and v is also given, and then you find the focal length. With proper sign convention you will be getting the answers. That is the meaning. So this is valid for both the mirror, for convex also and for concave also, right? And use the proper sign convention for both and use in this formula. So this is the mirror formula. Okay, derivation is also there, which involves concepts of triangles, like your congruent triangles or similar triangles, so that that derivation is not asked in the exams. So it's not we don't want to discuss it here. So let us now go to this magnification concept, the next part. Yeah, so let us see about magnification. So this magnification is very specific to mirrors. Okay, for mirrors, we are discussing magnification for mirrors. For lenses, there will be a separate case. For that, we will be discussing. Okay, now what is magnification? Generally, when we call it as, when say, where verbally, what will we call as magnified image? What will you call as the magnified case? You will call the magnified case as when image size is greater than object size, right? Then I will be calling it as a magnified case. Now I told that we represent the image size by, represent image size as h dash, and the object size as, h. Okay, that means, and if I am denoting this magnification by m, okay, so this is your m. Okay, so m is what? Image size. If I am telling that h dash is greater than h, then we are calling it as magnified image. Okay, and if image size is less than object size, right? Then we call it as what? H dash is less than h. That means this is diminished case or unmagnified or non-magnified case. Here magnification is occurring, here magnification is not occurring. So see this, we can say that if I take this h on the denominator side, what will it become? That means h dash by h is greater than 1. Okay, if I take this h down, here will be 1 only. Okay, this is an inequality relation, but you need to solve it. You can put it down just like an algebraic operation. Okay, so you put it down in the denominator. Here is only 1 left. So this is h dash by h is greater than 1. If I do the same thing here, you can say h dash by h is less than 1. So I can see that the ratio of this h dash and h, that is the image size and object size, ratio is greater than 1 or less than 1. Then we are defining magnification. So what we did, we termed magnification as h dash by h. That what is magnification? Magnification is nothing but the ratio of image size upon object size. This is the meaning. Okay, so when what is happening when this is h dash by h is greater than 1, that is when m is greater than 1, this is magnified. Magnification is happening. Magnification is happening. But when m is less than 1, that is h dash by h is less than 1, that is image size less than object size, that means m is less than 1, that means there is no magnification, rather the image is becoming diminished. So you can see that we now have a formula for this concept. In this way you can understand this magnification. So what we understood that, so magnification is nothing but ratio of image size to ratio of object size. Also, if we extend this relation, this is also governed by V by U, just put a minus sign in front of it. This magnification is for mirrors. Understood? This is for mirrors. Again, I am mentioning. Right. This is for mirrors. That is minus V upon U. Understood how this thing is coming? Right. So now let us discuss more on this formula. Right. So I told you that a second set of a relation for magnification with image and object distances. Okay. So now let us see this case, right? This is h dash by h, right? So I am telling that in the first case, I am told that if m is greater than 1, that means h dash by h is greater than 1, where magnification is happening, right? It means what? Second case we have magnification is less than 1, that means h dash by h is less than 1. So and if there is third case also, if m is equal to 1, what is the meaning? Then h dash by h means here h dash will be equal to h only, so that they will be cancelled and this will be becoming 1. So there is the object and image are having the same size. Okay, so these three cases you must know. Okay, this is regarding the this is regarding the this is regarding the sign of magnification. Can you comment something on this nature on this sign as well? Can you say something about sign of this? So this is with the magnitude of, I am seeing the magnitude of m. Now sign of m I will see. Sign of m is what? Suppose let us say consider a concave mirror, right? This is your pole and this is your principal axis. So this is your focus point, this is your C. So somewhere if you are putting an image C, suppose a case like this, right? So what was happening? The image was forming somewhere here, right? So in this case what happened? U was negative, see here, U is negative and this was your V. V is also negative. So if U is negative, V is negative, U negative, V negative. It means if you put in this formula, that is minus V by U, if U and V are negative, we will be left with this minus sign. So M will be negative. M will be then, M will be negative, right? M negative means what? It 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 governs a situation that M is negative. It means that the U and V, that the image and object are on the same side of the pole. That means the rays are actually meeting, and it means that the image is real. That means the sign of M, if it is negative, it means real image. You can verify in every case. Okay, when V is on the back side, obviously when virtual image will be forming, it will be on the back side of the mirror. As the image goes on the back side of the mirror, this V becomes positive. This V becomes positive. Okay, now let us consider the another case. right? Now let us see this one also. In let us see in the concave mirror itself, right? This was your principal axis. Let us say this is your pole and F and C. So when I put this object here, I was observing image somewhere here, right? Now if you see the distance, this is your U, this is U, but what is V? V is this. So in this case, U is negative, but V is what? Positive. Now again I will see the magnification formula, which is minus V by U. So V is positive, right? V is positive, U is negative, and there is a negative sign also. So this negative sign will be cancelled. You will be left with positive sign. So in virtual case, what we are observing is that M is positive. M is positive in case of mirror. So M is positive. It means it is a virtual image. It is a virtual image. So this much is the data which you can take from this magnification. Okay, which you can comment on the size of the image with respect to the size of the object, and seeing the sign of M, you can consider what nature of image is uh, uh, is formed by the reflection. What nature of image is formed by the reflection. So this is important. Now let me summarize. So this M represents magnification. So magnitude. So magnitude, that means amount. Okay, the numerical value. So the magnitude of magnification, it will tell you what is the enlarged, or rather you can find whether the image is enlarged or diminished. Okay, how you will be doing? M greater than 1 means enlarged, M less than 1 means same size, M less than 1 means diminished, or M equal to 1, that means same size. And sign of M means if it is negative, that means real and inverted image. I told you that real and inverted will be going hand in hand, real and inverted. And if it is positive, it means virtual and erect. So tell me, if I am telling you a mirror, a question is like that: a mirror has magnification M is equals to plus 1. Okay, M is equal to plus 1. Comment on size and nature of image. Okay, nature of image, size and nature of. So what will you answer? Suppose you are seeing the magnitude. What is the magnitude? M is equals to 1. That means nature of image is what? Image is same size as object. Same size of object. And what you can tell about size? Sorry, this was your size, that same size of object. And what you can call about the nature of image? Nature of image is what? It will be depending on the sign. What is the sign of M? Sign of M, you will see. Sign of M is positive. Positive means virtual. Virtual image. Right. So can you tell me which kind of mirror it is? Same size of the object. Image is same size of the object and virtual image. So in which mirror it has happened? So it is this mirror is a what? It is a plane mirror. So in plane mirror only, a plane mirror only, M is equal to plus 1 is observable, because same size of the object and virtual image. That is the case of a plane mirror only. Right? This is how you identify. Now let us take another example. Suppose M is equals to minus 2.5 is given. Now comment on the nature and size. So what is the size? First of all, magnitude, if you see, 2.5 is what? Greater than 1. So this is an enlarged case. Okay, enlarged case means size of the image is greater than size of the object. Now let us see the nature. Nature is what? This is a negative sign. negative sign, it means it is a real and inverted image. Okay, so this is how you can comment on the nature and size of image by just the magnification, but by just knowing the magnification, right? So this is how we will be dealing with this. Now if I tell you about a convex mirror, okay, consider this case also. In convex mirror, what happens? This is a convex mirror, this is a pole, right? And say this is your non-reflecting side, this is a convex mirror, right? In convex mirror, always the image is on this side only. On this side only the image is formed. Okay, so that is why m is equals to minus v by u, you know. So v will be positive always. V will be positive always and u will be negative always. So that is why one negative will get cancelled and m is always positive. That is why it will always give you a positive, means a virtual image. That is, a convex mirror always forms a virtual image. So that is what I am trying to tell you is that by the sign and magnitude of magnification, by the size, by the sign and magnitude of magnification, we can comment, we can comment on the nature and size of image. Okay, so in last I will draw a table also. Okay, okay, so this is magnification. Okay, and this is your right. So magnification is positive, negative. So then you will be commenting on the nature. So if it is positive, it is going to be a virtual image. This is for mirror only. Okay, virtual image. This is real image. And if I see the magnitude, m is greater than 1, m is less than 1, m is equal to 1. So this is the enlarged case, this is the size of image. Okay, so nature of image, size of image, enlarged, diminished, and this is same size. Okay, so you must remember these formulas which I am now mentioning. 1 by f is equals to 1 by v plus 1 by u. This is the mirror formula, right? And you must remember m is equals to h dash by h is equals to minus v by u, where you know what is v, what is u. H dash is size of image, h is size of object. So these two formula you must remember, and then we will be able to solve the numericals related to mirrors. So now this completes your reflection part. Now at last, let us see some of the uses of convex mirror, because we haven't seen this. So uses of convex mirror. So first of all, you know that convex mirror is like this, right? Convex mirror is like this. So you can see this field of view, you can see an area like this. This is your field of view of convex mirror. Okay, and in concave mirror, what is the field of view? It is not, and not more than this, it is up to this. And also in the plane mirror, the field of view is like this. So here the field of view is more, field of view is largest, right? And you can see the objects in small size, okay, diminished size. So we have wider field of view, you have wider field of view. That is why this convex mirror is used in rear view mirror of vehicles. It is used the rear view mirror of vehicles too, because the of the satellite side mirrors and the rear view mirror in the vehicles, in the cars we see, that is nothing but a convex mirror. Because what is happening, since it has a wider field of view, this reflecting surface has a wider field of view, it will, on a small piece of mirror, you will be able to see more of the area of the back side. So that is why this rear view mirror, it is used as a rear view mirror in vehicles, right? Another use of convex mirror we see in the parking mirrors, okay, or security or parking mirrors. You must have seen that on the, suppose here is a circle, these are four roads are coming, okay, like this, okay, or we have a road like this, right? We have a road like this, right? This is, let us take this case, we have a road like this, so this is your road. So vehicles can come from this side also, come from this side also. So suppose a vehicle is coming from this side, okay, and suddenly they have to take a turn. So they don't know what is on this side. So what will we do? We will place a large mirror like this, red colored. Generally, these mirrors are placed like this. A big mirror is here. This is a traffic mirror. So what it will provide you? It will provide you the view of this side also. It will provide the view of this side also. So you will be able to see if any vehicle is coming from this side. So that is, it is used in a security mirrors. In shops also, sometimes what has happened, today we are equipped with CCTV cameras and all. Sometimes what happens is, to give, suppose there is a supermart and there are one lane like this, one lane like this, here shop items are being kept, one lane is like this, one lane is like this, people can enter here, this is again things, one lane. So what will we do? They will put a mirror here, okay, and suppose a large mirror they will be putting here, and from this side a person will be able to see if anything is not being stolen by someone or somewhat, so he can observe on this mirror. So it is used as a security mirrors, okay. So these are the major uses of convex mirror, that is in the rear view mirror of vehicles, and it is used in the security mirrors. Security mirrors also we are using, okay. And then for general purpose, you can understand that this is a divergent kind of a mirror, because what will be happening always in this convex mirror, this side is your non-reflecting side, this side is the reflecting side. So wherever the rays are coming to this mirror, whenever the rays are coming to this mirror, it will diverge these. So in any case, if any of the case, if you want the light to be scattered around all the place, then we can use convex mirror in that particular example, okay. In that particular case we can use this. So majorly it is used in security mirrors and parking mirrors also, okay. Security mirrors, traffic mirrors you can say, or rear view mirror of the vehicles is the most important use of this convex mirror, okay. So basically this larger field of view, we take advantage of this, and this larger field of view, this larger field of view from this area, we can completely see up to this area. So that is the major use of convex mirror. So this on and whole completes your reflection part, okay. The reflection part is now completed, and the next class we will be seeing some numericals related to this reflection portion involving plane mirrors, concave and convex mirrors. So this completes your reflection part, and now we will see the numericals, and then we will move to refraction.